Today we are going to do the lab of Dsp Lab 2. The objective of this lab is signal representation. Now, having a look at the task 1, we are going to first define the parameters n0, n1, n2 with the index vector ranging from n1 to n2. We are using the stem command here, which plot the n vector against the x. The x is given n minus n naught greater than equal to 0. When we run this code, we get this output. Now moving on to the task 2. Same we have like we did in task 1, we are going to do almost the same thing, just we are replacing x is equal to n minus n naught equals to 0. Then we are going to use the stem command, which is used for the plotting of the signals, and we get this output. Moving on to the task 3, here we have two parameters, n1 equals to minus 3, n2 equals to 3, and the signal given to us is x is equal to 3 into 0.5 raised to the power n, and we use stem command again to plot n against x, so we get this output on the first half. So this is the output that we get from that code. Now replacing the x with 3 cos 3 pi n plus 5, and then running the code again, we get that sinusoidal signal. Moving on to the task 4. In this task we are going to define the unit impulse function. First we will initialize the impulse sequence, then we set the value at the first position to 1. We have using this code as an example, n equals to 10 and k is equal to 5. Then we have called the signal impulse sequence and then used the stem command to plot the signal against each other, and we get this output. Moving on to the task 5. In this task we have asked to define the step sequence, like in the last task we have did the unit impulse sequence. So in this task we have to do the step sequence. This function allows you to easily generate a unit step sequence by specifying its length and the position where the steps start. For example, we have taken the code where n equals to 10, k equals to 5, then we called that function we have defined earlier as a name goes by step sequence. This code generates a unit step sequence of length n with the step starting at index 5 and then plot the result using the stem function. So we get that output from that. Moving on to the task 6. In this task we have given a signal which is xn is equal to un minus 3 delta n minus 1, and we have to get the impulse response and step response of that signal. As we know earlier that we have already defined the functions of step response and impulse response, so we will call that signal again simultaneously. When we call the unit impulse signal function, we have get that output, and when we call the unit step response of that signal, so we will have that kind of output when we run the code. There is also the second function which is given, and that signal is 3un minus 3 plus delta n minus 2 plus un. So we have to get the step response and the impulse response of that signal also. We are using subplot, so we can get all of the step responses, impulse response on the same graph. As we can see in this output, on the top we have the input signal, and then we have the unit impulse response of that signal, and then at the end we have the unit response of that signal by calling the functions we have already defined earlier to get the unit step response and unit impulse response. Moving on to the task 7. In this task we have to flip the signal. So we first define an example signal, then we flip the original signal using the flipper function. Then we use the subplot for displaying the original and flipped signal. Stem command plot the original and flipped signal using the stem function with different colors and line widths. Labels and titles are added to each subplot for better implementation. When we run the code, we see two subplots representing the original and flipped signal. The original signal is shown in blue and the flipped signal is shown in red. As we can see there, the original signal is in blue and the flipped signal is in red. Now moving on to the next task. In this task we have to scale the function. So what we did in that task is we first defined an example signal, then specified the amount by which the signal will be scaled. Then we compute the scale indices based on the original signal length and the scale factor. In this case, the signal itself is not scaled, only the indices are scaled. Then we use the subplots for displaying the original and scaled signal. The original and scale signal using the step function with different colors and line widths. Label and titles are added to each subplot for better implementation. When we run the code, we see two subplots representing the original and scale signal. The original signal is shown in blue and the scale signal is shown in red, as we can see here in the output. The original signal is in blue, and then when we scale the signal, we have the output in the color red. Moving on to the task 9, in this task we have to shift the signal by amount 2. So what we did in this task, that we first defined the example signal, then we specify the amount by which the signal will be shifted, then we perform circular shifting of the originals using the circle shift function. Then we use subplot for displaying the original and shifted signal, plot the original and shifted signal using the step function with different color and line widths. Labels and titles are added for each plot for better implementation. When we run the code, we see two subplots representing the original and shifted signal. Again, the original signal is in blue and the shifted signal is shown in red. As we can see here, this is the original signal, and when we shift the signal, we have the output like this. Now moving on to the task 10, in which we have to find the zero hold of the signal. First we define the time vector for the continuous time signal, then we specify the time period for the discrete time signal, define the time vector for the discrete time signal, initialize the discrete time signal. The loop performs zero order hold by finding the nearest time point in the continuous signal for each sample in the discrete signal. Results are plotted using the plot and stamp function with different colors and line width. When we run the code, we see two subplots representing the continuous time signal and the discrete time signal obtained using zero hold. Like that. Out top we have the continuous time shifting function, and then we have the zero hold discrete time function. We have converted the signal from continuous into discrete form. Now moving on to the task 11, which is the last task of this lab. In this task we have to find the first order hold of the signal. Again we have to define the time vector, then we have to define an example continuous time signal with time period of 0.5 seconds. Then we initialize the discrete time signal, the loop first order hold by interpolating between adjacent points in the continuous signal. Results are plotting using the plot and stamp function with different colors and line widths. When we run this code, we see two subplots representing the continuous time signal and discrete time signal obtained using first order hold. Like this, we have the continuous signal, and then when we use the first order hold, we have that kind of discrete output. So that is all for the lab number 2. Thank you for watching.